exercise booklet out. You'll get out your speed drill and review exercise booklet. Turn to page 6. Page 6. And I want to go over exercise 5 with you and refresh your memory on some things that you should have learned last year in 7th grade. Pause the video while you find your booklet if you don't have it handy. As you look at exercise 5 there at the top of page 6, you notice there a little bit of a blurb which we'll go over together. It says that gross pay refers to the amount of money that a person earns from his employer. From every paycheck, however, taxes are deducted, included federal and state income tax, Medicare tax, Social Security tax. It does mention these last two taxes. The Medicare and Social Security tax are called FICA taxes. Federal Insurance Contributions Act formed these two, sometimes called entitlements, though you do pay into them, so you truly are really entitled to them because you paid into them. But anyway, Medicare and Social Security you pay for to take care of the elderly. Personally, I believe I ought to be able to choose whether or not I want to give to help the elderly. But the government has decided to make that choice for us and is promising in return that when we are elderly, they will take care of us. That is a lie, by the way. The rate things are going, there will be nothing in Social Security for me or Medicare for me when I'm old, but I have to pay it anyway. And it's just whatever you have to do. The amount of money that a person receives after taxes are deducted is called net pay. So for instance, you might get a paycheck that says, congratulations, you made $3,000 at the end of these last 2 weeks. And you look in your bank account and there's $2,100 there. And you're like, I'm $900 short. Yeah, Uncle Sam took it. It's called taxes. Okay, so gross pay is how much you should be getting, and then net pay is how much you actually get by the time the taxes are deducted. So I've got a couple of problems for you to work here. The first two problems are tied together, and the third problem is a separate one. I want you to pause the video while you work those three problems, and then restart the video, and I'll go over the answers. All right, let's go ahead and take a look at the answers that you got for these three problems on exercise 5. It says Brooke Adams gets paid $7.25 per hour by her employer. This is or was at least minimum wage at one point. She worked 20 1/4 hours last week. Find her gross pay. Well, we're going to take the 20.25 hours, and we're going to multiply that by $7.25 per hour that she should be earning. And when you multiply all of that out, and you'll notice there's going to wind up being 4 decimal places here, so we're going to have to round on this. And we wind up with 4 decimal places, $146.81.25. This is not sufficient to round up, so we're going to say $146.81 is her gross pay. However, part 2, if Brooke had $42.39 withheld from her paycheck for taxes, find her net pay. Well, if it's withheld from her, we have to subtract away taxes. So she earned $146.81, but $42.39 got taken away by the government. So how much does she have left? $104.42 is her net pay. This is what actually goes into the bank. This is what she worked hard for. That's what the government decided they deserve for doing whatever it is the government does. Now, okay, before I'm too hard on the government, okay, for the record, yes, the government pays for a military that watches over us. It pays for the governmental officials to meet, congregate, and make sure that laws of our country are appropriate, sort of. It pays for a police force that cares for us when we need it. It pays for firefighters in most municipalities that are there to protect us in case we need it. So there are some legitimate, the Water Commission, trash pickup sometimes is a governmental agency that comes through and takes care of that. So there are governmental agencies that take care of things that we need. So, lest we be too harsh on the government, there are things that need to operate, but there's an awful lot of waste that the government does as well. Let's take a look at the last problem. It says David Almers earns a salary of $465 per week. That would be his, which, gross pay or net pay? Well, if it's what he earns, it's his gross pay. If it's what he receives, it's his net pay, right? You earn the gross, you receive just the net. From this, it says $48 is withheld for federal income tax. $61 is withheld for state income tax. So federal would be US of A, state is Georgia, for instance. Some states, by the way, don't have income tax. I grew up in Florida. Florida doesn't take any of your income, but Georgia does. Alabama also does. And $35.57 is withheld for FICA taxes. That would be your Medicare and your Social Security. Find his net pay. Well, pretty much, we could add up the $48, the $61, and the $35.57. And all told, the government here is taking $144.57. That then we would subtract from the $465, and we'll find that he is left with $320.43. $320.43. Hey, if you got all three of those correct, have your parents shoot me an email letting me know that you got all of the review exercise problems correct. All right, go ahead and set that aside for now. And I want to take a look at the homework that you did last night. Turn in your textbooks to page 93. Turn in your textbooks to page 93. Let's see how you did on the homework. Number 1 on the homework. When converting from kilograms to milligrams, which way does the decimal move? Well, remember King Henry died unexpectedly drinking chocolate milk. So to go from kilo to milli, we have to go to the right. Number 2, convert 4 tablespoons to teaspoons. It adjusts teaspoons. Well, remember, there are 3 teaspoons in every tablespoon. So if I have 4 tablespoons, that's 4 sets of 3, or 12 teaspoons, plus the 2 teaspoons I already started with, 14 teaspoons. Number 3, how many conversion factors are needed to convert from days to seconds? Well, we actually did a problem, I believe, the other day that was days to seconds. So remember, you'd have to put the days over 1. You'd need to multiply by, let's see here, 24 hours, that's in hours, in 1 day. That gets the days to cancel. You would need 60 minutes to an hour. That gets the hours to cancel. 60 seconds to 1 minute. And that would leave you with seconds. So 1, 2, 3 conversion factors. This wasn't one of those. This is what we started with. So 3 conversion factors would be needed. Number 4, is 5.9 times 10 to the negative third written in correct scientific notation? Why or why not? Yes, it is, because there's only 1 digit before the decimal place. Number 5, express those numbers in scientific notation. Well, for number 5a, you can only move the decimal 1 place to get to 0.6689. And since you moved it 1 place that way, we'd say times 10 to the first. For the next one, we move the decimal over to get 1.2. You move it 3 places backward, times 10 to the negative third. And there would be our answers for A and B to number 5. Number 6, A and B, converting to standard form. Well, on letter A, we need to move the decimal to the left to make it a small number that would be less than 1, 0.0547. And then for the other, to the right, to make it a number greater than 1. Move it 3 places, meaning and you end up tacking on 1 0, 1,110. For number 7, 16 quarts, 2 pecks, divide by 8. Number 8, 640 cups. You need to use dimensional analysis here. Convert the cups to pints, that's 320. Convert the pints into quarts, that is 160. And convert the quarts to gallons, that's 40 is your answer. So using dimensional analysis, you end up with 40, or you do a series of conversions. Number 6, 0.014 hectoliters is how many liters? Well, you have to go from Henry to unexpectedly, because liters is the unit. Well, that means moving the decimal 2 places that way, which gives you 1.4 liters. Number 10, when you add it up, you initially get 11 cups, 9 fluid ounces, but remember, it only takes 8 fluid ounces to make a cup. So of the 9 fluid ounces, take 8 of them. That gives you a 12th cup and leaves you with only 1 fluid ounce. So 12 cups, 1 fluid ounce. Number 11, you divide. 8 goes into 56 times with 2 pounds left over. Those 2 pounds convert into 32 ounces. Plus the 8 ounces you already had, 40 ounces, which divided by 8 is 5. So 6 pounds, 5 ounces, your answer. On number 12, you multiply by 20. Oh my goodness, we end up with 320 gallons, 40 quarts. But remember, it takes 4 quarts to make a gallon. Well, if there's 40 quarts, that's 10 gallons, which adds on to the 320 to give you an even answer of 330 gallons. And number 13, when you subtract, well, first you have to borrow, right? Borrow 1 of the hours, a way to give you 49 hours. Then that 1 hour becomes 60 minutes, which tacks on to the 20 to give you 80 minutes. Subtracting it 30 minutes, 43 hours. Your answer is 43 hours, 30 minutes. Jumping down to number 19 from your homework. During a 4-person relay race, the team's average time for each runner was 1 minute 20 seconds. What was the total time for the team? Well, if there's 4 people in the relay race, and on average they run 1 minute 20 for whatever it was they were running, maybe it was 1 lap around the track, which isn't real fast, but it's, you know, for junior hires maybe, not real bad either. End up with 5 minutes, 20 seconds, you multiply by 4. 5 minutes, 20 seconds, you multiply by 4. Remember, if you're finding an average, you divide the total by how many there are. But if you know the average, you multiply by how many there are to get the total. Number 20, if the height of a redwood tree is 126 yards, what's its height in inches? Just multiply by 36. 4,536 inches would be the height of the redwood tree. All right, if you had any questions on the homework, be sure to have your parents shoot me an email, and I will arrange to video chat with you later and give you the help one-on-one that you need. I want you to turn over now to page 84. And I had you read last night about something called significant digits. This is something you're going to talk about in physical science, chemistry, physics, basically when math begins to creep into your science classes and truly become the language of science, which you've heard your whole life. Math is the language of science. Math is and you're like, I never do any math in science. Oh, you will. You will do some math in science. In fact, in your STEM project, you'll do some math with it, won't you? And as you do work in your STEM project, you're going to have to take measurements of some kind, whether you're measuring time, whether you're measuring height, whether you're measuring weight, whether you're measuring a certain volume of something. You're going to have to take some measurements in your STEM project. And as you do, there are all different kinds of instruments that you could use. The book uses an illustration of 3 different scales that can weigh the same thing. They weighed a bunch of sugar. They weighed 227 grams of sugar. One of the scales read 227.0. Now, on one hand, we look at the 0 and we say, who really cares about the 0? Well, by putting it there, it shows us, no. We didn't just say, for instance, 226.8, that's pretty much 227, right? By saying 0.0, we're saying, no, really, 227, like that much exactly. To the nearest tenth of a gram, that much. Or we might say, well, that's pretty much 230 grams. Well, if you're rounding to the nearest 100, that would be 200 grams. Do you see how certain numbers are less exact than others? 227, for instance, could even be a rounded value, rounded to the nearest whole gram. Rounded to the nearest 10 grams, rounded to the nearest 100 grams, or rounded to the nearest tenth of a gram. Basically, the more digits that you see, the more exact, the more accurate your number really is. And significant digits help us to show accuracy. And here's the most important takeaway from all of it, is that as you do calculations, as you average out things for your STEM project, as you work with different quantities in science, you want to make sure that an answer you get from a calculation isn't more exact or accurate than numbers you started with. Let me give you an example. Let's suppose we had a rock, and we measured the rock on a toy scale. And the toy scale told us that the rock was 82 grams. That was its mass, or we would say its weight, which is pretty analogous to mass. So an 82-gram rock. But let's suppose we had a super, hyper-accurate scale from the science lab, and we weighed the same rock, and it said it was 82.103 grams. Do you realize this is not entirely inaccurate? It just doesn't show quite as exact of a measurement, right? How much is the rock? Is it a lie to say it's 82 grams? No, it's 82 grams pretty much, right? You want a more exact number, okay, 82.103 grams. Do you see that this number carries with it more detail, as it were, than this one. This has more significant digits in it than this one. Okay? Now, if the rock were really, truly, like it was actually 82 grams, then the super scientific scale would have said 82.000. And you look at these and you say, well, Mr. Nadesky, these are the same thing. Mathematically, yes. To a scientist, they're not. To a scientist, if I get a scale that says 82, I'm like, well, it could be 81.9, could be 82.3, but it's 82 when you round it. But when my scale actually shows me these zeros, I'm like, wow, it came to exactly 82. For instance, if you go to the store and you were to buy a gallon of milk, and the gallon of milk was listed at $3.97, and you said, Mr. Dasky, how much does it cost for a gallon of milk? I'd say it costs $4. Is that a lie? No, it's not a lie. It pretty much costs $4. But if I were to say, Mr. Dasky, how much is it for a gallon of milk? $3.97. You'd be like, how do you know that? When I say $4, I'm telling you pretty much $4. And you're like, okay, that's about how much it costs. And when I say 4, you know I'm probably rounding. It could be like $3.86, $4.10, but it's around $4. When I say $3.97, I'm being very detailed here. Have you ever been to a store, gotten your receipt, and your receipt came to like, I don't know, $23 exactly? And you're like, whoa, it came out even. Okay, you're shocked because receipts normally don't come out even, right? They normally come out with something else. Or perhaps you've seen your parents at the gas pump. Click, 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 ah! Okay, why? Because they just made their total $25.01. And they were going for 25 even, okay? To say that they paid $25 isn't a lie, they did. When you round to the nearest whole dollar. Unfortunately, they didn't want to just round to the nearest whole dollar. They wanted exactly $25.00. Okay? Some parents don't obsess over it, some parents do. But you get the idea that when these come out with zeros, that's more significant than just saying, I paid $25 to fill up on gas. That's still true. You did pay $25 to fill up on gas. I mean, who cares about the penny, right? Though it does drive you crazy if you're, one of those OCD people like me. So coming back to the original problem here, significant digits show us how exact something is. Let's go back to our rock for just a moment. We would say right now that this particular number has 2 significant digits, or significant figures is a term I'll use quite often. Because I'm lazy, I'll say sig figs. Significant figures, sig figs. Okay, I'll use that term because I'm lazy. So when I say sig figs, you know I'm talking about significant digits or significant figures. This, however, has 1, 2, 3, 4, 5 sig figs. It is a more detailed, it is a more accurate, it is a more exact number. Let's suppose we wanted to measure the density of our rock. Now, density is how much stuff is packed in. For instance, you ever picked up a box and you're like, hey, that's really light. And you pick up the exact same box again, like, oh, that's heavy. It's the same size box, right? And because it was the same size, you just imagined they would weigh the same. I think of Abeka book boxes. We get a ton of it, well, hundreds, I should say. That is about a ton, actually. We get a little over a ton of Abeka books every year for our school. And all of the boxes, I should say a lot of the boxes, are the same size. And when they fill the boxes, they put some books in there, and they wrap them in plastic, and they sit there in the box. And every now and then you'll get a box that, let's just say, is about so big in cross-section, and the books are plastic wrapped like this. There's a lot of empty space. Then we'll get another box of books that is like this, and it's literally, it is completely filled. There is no empty space at all. These 2 boxes may weigh the same amount. Meaning there's the same amount of stuff inside. But this one looks bigger, so you would think it would be heavier. So when you pick it up, you're like, oh, that's not bad. You pick up this box, which looks smaller, so you think it would be lighter. You pick it up, like, oh, dang, that's heavy. It's not heavy. It's the same weight. But because there's less volume to it, it looks like it should be lighter, and therefore it is denser. Density is the mass of something divided by its volume. That's not something you have to memorize, but if I want to know the density, I have to divide by the volume. Well, let's suppose I had some cool gadget that could measure the actual volume of this. And we measured it to be 42.913 cubic centimeters. Now, a cubic centimeter of water is a milliliter. Okay, a milliliter of water would fill a cube centimeter of water. So knowing this, let's suppose I took my rock and I dropped it into something that had 300 milliliters of water in it. And I dropped the rock in. And the water level, as you know, if you drop something in the water level goes higher. And let's suppose the water level goes up to 344 milliliters. Then based on how I'm reading it, it looks like there are 44 milliliters or cubic centimeters of volume. Okay? And so notice these two numbers are pretty similar. I mean, for doing this kind of an eye test with water versus a high-tech gadget, I'm only about a cubic centimeter off, right? This is pretty much 43, only a cubic centimeter off. Well, let's suppose I wanted to find the density. And so since I'm lazy, I'm not doing this by hand. I'm pulling out my calculator. And I say 82 divided by 44 is 1.8636 blah, blah, blah cubic centimeters. I'm like, wow, that's a really detailed answer. Come over here, 82 divided by 42, or excuse me, 82.103 divided by 42.913. And here, I did something wrong, try that again. There we go. And I get 1.91324 blah, 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 grams per cubic centimeter for the density. Those really aren't too far off from each other, are they? I mean, 0.05 is all they're off. Very similar. And these were with just kind of rough guesstimates or crude instruments. These were with the really sciencey things. But here's the deal. Do you see how this answer looks really detailed? So what's the density of your rock? Well, according to my calculations, the density of my rock is 1.8636 grams per cubic centimeter. Look at how many significant digits are in the answer. Do you see that the answer looks really super detailed? But the numbers we started with weren't super detailed. Do you see how these numbers were super detailed and the answer is super detailed? Here's the key. In science, your answers are allowed to be just as super detailed as what you start with. 2 sig figs, 2 sig figs. I'm only allowed to express my answer with 2 sig figs. 1, 2. Now the 6 will bump this up and we'll say 1.9 grams per cubic centimeter. But it would actually be wrong to a scientist to say that it's 1.8636 blah, blah, blah. Because you don't know how can you possibly get that level of detail, that level of accuracy, that level of exactness when you started out with numbers like those. But over here, I would expect quite a bit of detail. I would expect 5 digits of detail because I had 5 digits of detail to begin with. Does that make sense? Now, my 4 does not round the 2 up. So I'd say my answer is 1.9132 grams per cubic centimeter. Now, you're not going to have to do all of this in 8th grade math, but I wanted to introduce you to the idea of significant figures. What we want to start with, though, is just teaching you as an 8th grader. I wanted to show you why it works and how it works. You're not going to be tested on that, so stop panicking. All right? What I want you to learn, though, is how to figure out how many significant digits you have. Look at page 85. First of all, any counting number, any counting digit, 1, 2, 3, 4, 5, 6, 7, 8, or 9, is always going to be significant. So if it's not as, basically anything that's not a 0, okay? Now what about zeros, though? Well, if you have a 0 in between counting numbers, like this 0 right here, it is also significant because there's another digit after it that helps to make it significant. So if I had the number 2007, If, for instance, if you said, hey, Mr. Nadaski, how many people went to the basketball game the other day? And I said 2007. You'd be like, oh, wow, you counted? Or did you look at the attendance report? How did you know there were that many? You were probably expecting me to say, oh, probably somewhere around 2,000. Do you see that around 2,000 is a very general number? 2007 is very specific. Well, this digit is specific, and it's specific because these digits exist, right? This digit couldn't be here if it weren't for these place-holding zeros. So we would say that there are 4 sig figs in that number. Zeros that are in between counting digits, or 1 through 9s, are significant. You see that there in the second box. And if you were to have them, remember the illustration a moment ago, to the right-hand side, and there's a decimal in the number, they are also significant. Just like when you step on the scale and you see that you weigh 130.0 pounds. My scale at home shows to the 10th. Now, unfortunately, I haven't seen 130 in a long, long time at this point. But 130.0 pounds. You're like, wow, hey, Mom, well, you might not be happy about it. I don't know. Hey, Mom, I'm exactly 130. Or even thinking to yourself, wow, it's exactly 130. That's cool, right? Because it really is. Both of these zeros are significant because there's a decimal in the number. Or even if you had a scale that said 200 point. Because you see, that's not the same as 198. 198 would round up to 200, but that would be rounded to the nearest 100, or even rounded to the nearest 10. The fact that there's a point here tells me it's rounded to the nearest ones place, to the nearest whole pound. So also you see there that zeros that are to the right of the counting digits, if there is a decimal somewhere in that number, the zero is significant. So when are zeros not significant? Well, zeros that start the number. Zeros that are literally just a placeholder, 0.0004. That's the only digit that's significant. Now, it still sounds really, really detailed, but you know, it's not so much. There's only the one digit of significance. None of these zeros matter for anything other than placeholding. 1 sig fig. Or if there isn't a decimal in the number, well, now we assume it's rounded to the nearest 100. So there's 1 digit of significance. So if there's not a decimal, zeros off to the right-hand side, they're not significant. And zeros to the left of the number because of a decimal, they're never significant either. Look at the example at the bottom of page 85. How many significant figures are in 3,200? Well, you know, first of all, the 3 is significant, the 2 is significant. The only question mark is, what about the zeros? Are they to the right or to the left, class? They're to the right. Now, if they're to the left, it's an immediate no. If they're to the right, they could be significant if there is a decimal. No decimal, they ain't significant. 2 sig figs. However, if it said 3,200 point, now there's a decimal. Now how many sig figs? 4 in the number. Look at the next number, 401.20. How many significant digits? Well, you know the 4, the 1, and the 2 are all significant, correct? The question is, what about the zeros? Notice the first 0 is in between 2 counting numbers. What's the rule if it's in between? Always significant. So that one's definitely in. There's 4. And there's 1 all the way to the right-hand side. Remember, if it's to the right, it's only significant if there's a decimal. Is there a decimal in the number? So is it significant? 5 sig figs. Your job in the homework was to answer numbers 1 through 12. I'm curious how you did. Now, if you didn't do well, that's okay. Okay? We hadn't talked about this yet. But now that we've talked about it, let's see how we did on the homework. The question is the underlined digit significant? I'm going to go through the answers. You check. It also said to explain why or why not. There's a lot of ways you could word it. I'm going to give you my wording. Number 1, is the 4 significant? Yes. 4 is always significant, as is 1, 2, 3, 5, 6, 7, 8, and 9. Always significant. Number 2, is the 0 significant? Yes, because it's in between 2 numbers that are not zeros. Number 3, is the 0 significant? Yes, because even though it's to the right, it has a decimal in the number, so it's significant. Number 4, is that 0 significant? No. There are no counting numbers before it. It is to the left of the first counting digit. So, nope, not significant, ever, ever, ever. Number 5, is that 0 significant? No, there's not a decimal. It's to the right, which means it could be if and only if there were a decimal. Ain't no decimal, ain't significant. Number 6, 9 is always significant. Number 7, 0. Yes, because again, it's between digits. There are counting numbers on opposite sides of it. It's in the middle somewhere. Number 8, yes, because there is a decimal in the number. So even though it's to the right of the last counting digit, there's a decimal in there somewhere, so that makes it significant. Number 9, that 0 for the same reason as number 8. It's to the right, but there is a decimal in the number, so it is significant. Number 10, yes. Now, it's not directly between two counting digits, but there is a counting digit somewhere before and somewhere after. For instance, in the number 2007, these zeros are significant because they are between two counting digits. So, although there are 3 zeros in a row, there's a 4 before the set of 3, there's a 3 after, plus there's a decimal in there anyway, but yes, all of those zeros are significant in there. Number 11, no. It's at the beginning of the number, it's to the left, if you will, and that means it's never significant. For instance, if I said, Mr. Deskey, how many students are in your pre-algebra class this year? Well, we don't have very many. We only have 3. Do adding zeros before the 3 matter? No, not unless you're marking a standardized test form and you have to fill in all 4 spaces. 3, it's the same thing, right? No, zeros to the left or before a number, you might say never significant. And number 12, no. It's to the right, but there's not a decimal point, which leads us to believe we rounded to the thousands place, so the 4 is the last digit of significance. If you got them all correct, let me read through the answers one more time very quickly. Yes, 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 no, no. Yes, 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 no, no. If you got all 12 right, have your parents shoot me an email with that information. Real quick, I want to go through these with you and let's see, can you tell how many digits are significant? So what I'm going to do is I'm going to go through these one at a time, and I'm going to pause for a moment. You can either jot your answer down very quickly, or you can pause it real quick, write your answer down, and then unpause. Number 1, there are 5 significant digits. All 5 digits are significant. Number 2, 6 significant digits. All of them, again, are significant. Number 3, 6 significant digits. All 6 digits have significance. Number 4, 3, 2, 5, and 7 are significant, but none of the zeros before are. Only 3. Number 5, 2, the 3 and the 7, but because there's no decimal, the zeros are not significant. Number 6, 8 significant digits. Yes, every single digit there is significant. Number 7, 4. 4 digits of significance. They're all significant. Number 8, all 4 are significant again because of that decimal point. I know they're to the right side, but there's a decimal in there, so all those zeros become significant. Number 9, once again, all 8 digits have significance because that decimal there, and of course the other zeros in between. Number 10, 9 digits of significance. Again, since the zeros fall in the middle of other counting numbers, they're all significant. Number 11, 1. All the zeros you see are before the 5. Zeros before never matter, so only 1 digit of significance. Number 12, 3 digits of significance. Hopefully, after running through that, it makes sense to you. What I want you to do now is 13 through 23, the odd. 13 through 23, the odd. You're doing the same thing. You're telling me how many digits are significant. You can pause the video. All right, let's take a look at your answers on 13 through 23, the odd. Number 13, 3. Number 15, 1. Number 17, 3. Not the 2 before, But because there's a decimal, the 0 at the end is, but not the zeros before. Number 19, 4. The 0 in the middle, yes, but the zeros at the end, no. Number 21, 4. The first two zeros are not because they're before the number. The next 0 is in between, so it is. And number 23, 1. If you're good to go, move on and do numbers 14 through 24, the even. 14 through 24, the even. If you're not good, you may want to shoot me an email and pause the video where we're at. After I've had a chance to help you later on this afternoon, you can go back and watch the end of the video. Either way, go ahead and pause the video until you're finished. All right, let's take a look at your answers for 14 through 24. Number 14, 4. Number 16, 2. Number 18, 3. Number 20, 2. Number 22, 1. And number 24, 7. If you got them all right, I think you're good to go. If you missed some of those and you're like, oh, that's what okay, yeah, I got it now. That's fine, go ahead and we'll stay with the video. But again, if you're struggling with this, pause the video and send me an email and I'll contact you later and help you with this before you move on. But if you're good, I want you to go on and do the homework section 1 through 14. Go ahead and pause the video here and I'll go over the answers once you're finished. You can unpause. All right, let's take a look at the homework section 1 through 14. Number 1, yes, it's a number 1 through 9. Number 2, no, it's a 0 before the number or to the left of the number. Number 3, no, it's a 0 to the right of the number and there's not a decimal. Number 4, yes, there's a 0 but it's in between digits. Number 5, yes, it's to the right or after the last counting digit, but there's a decimal, so that makes it significant. And number 6, yes. Now, although the 0 isn't right between two counting numbers, there's a set of 4 zeros altogether. Counting number on one side, counting number on the other side. All those zeros are significant, including the one that was underlined. For number 7, there are 3. Number 8, there are 2, 9, 3, 10, 1. Number 11, 4. Number 12, 3. Number 13, 5. And number 14, 8. Hopefully you got those. Again, if you struggle with that, shoot me an email. I'll work with you. I'll be happy to help you understand that. Your homework for this evening has nothing really whatsoever to do with significant digits. That was just a help you understand this concept, maybe a little of that on the exam coming up next week, but primarily the point is help you understand this before you get to science class next year. All right, for your homework this evening, I need you to do pages 90. I say pages 92 to 93. I think it's all on page 92. Yeah, it's all on page 92. Page 92, numbers 1 through 24. Page 92, numbers 1 through 24. All right. Again, any questions? Let me know. I'll be sure to help you out. Otherwise, have a wonderful rest of your day.